From a note so deep it took 240 million years to complete one wavelength to a death so slow your own body would watch it happen to itself. These are the most disturbing facts about black holes ever discovered. And we begin with the one almost nobody knows about. Black holes have a sound.
In 2003, NASA's Chandra X-ray Observatory pointed at a supermassive black hole sitting at the center of the Perseus galaxy cluster, 250 million light-years away. What it found shouldn't have been possible.
Sound cannot travel through empty space. There's no air, no medium, nothing for the wave to move through. But the Perseus cluster isn't empty. It's filled with scorching hot gas, and that gas was rippling outward from the black hole in real physical pressure waves. Astronomers translated the pitch of those waves into a musical note, a B-flat, 57 octaves below middle C. To put that in perspective, a piano only spans about 7 octaves total. This note is so deep that a single wavelength takes roughly 10 million years to complete. You could not hear it even if you pressed your ear directly against the galaxy cluster. It is, quite simply, the deepest sound ever detected in the universe, and it has been humming, unbroken, for longer than our species has existed. But a sound that takes 10 million years to finish is nothing compared to what happens to time itself once you get close enough to look inside one.
Get near a black hole, and time starts behaving the way you think it does. The closer you get to the event horizon, the slower time moves for you relative to someone watching from far away. This isn't a feeling or an illusion. It's been measured, tested, and confirmed. If you hovered just above the event horizon of a black hole for what felt to you like 1 hour and then flew back out, you could find that decades or centuries had passed everywhere else in the universe. Your friends, your family, your entire civilization could be gone by the time you returned, while you'd aged a single hour. And here's the part that breaks most people's intuition. From your own perspective, falling in would feel completely ordinary, right up until it didn't. But if time itself bends this violently near a black hole, the natural question is what an outside observer would actually see happen to you. And the answer is something that still unsettles physicists today.
If a friend watched you fall toward a black hole from a safe distance, they would never actually see you cross the event horizon. As you approached it, time dilation would stretch your final moments out and longer, your image growing dimmer and redder, slowing down more and more, approaching that boundary in smaller and smaller fractions, but mathematically never quite arriving. To them, you would freeze, a faint, frozen silhouette stuck at the edge forever, fading until it's too dim to detect. Meanwhile, in your own experience, you would have already crossed that line in seconds and continued falling. Two completely different realities, both equally true, depending entirely on where you're standing. But even this isn't the most disturbing way a black hole distorts reality. Something it does to the universe itself that sounds
more like a glitch than physics. Cross the event horizon of a black hole, and something happens that has no everyday equivalent. Outside, you can move freely through space, but time only moves forward. Inside the event horizon, the roles swap.
Space becomes as fixed as time used to be, and the singularity stops being a place and starts being a moment. You're not falling toward a location anymore. You are falling toward a point in your own future, the same unavoidable way you're currently falling toward next Tuesday. There is no direction you could travel, no engine powerful enough that would let you avoid it. It isn't in front of you. It's ahead of you in time, and time, by definition, only moves one way. But while the inside of a black hole rewrites the rules of space and time, the outside of one is busy rewriting something else, matter itself.
Fall toward a black hole feet first, and the gravity pulling on your feet would be measurably, dramatically stronger than the gravity pulling on your head.
This difference is called a tidal force, the same basic effect that causes ocean tides on Earth, except magnified into something lethal. As you got closer, your body would begin to stretch, slowly at first, then catastrophically. Eventually, the tidal force would exceed what your body could physically withstand, and you would separate. Not explode, not vaporize, but pull apart at your weakest point, then pull apart again and again in a chain reaction lasting only seconds until you were reduced to a thin stream of disconnected atoms spiraling into the dark. Scientists with a strange sense of humor for something this gruesome call this spaghettification. The smaller the black hole, the faster and more violent this happens. Near a smaller stellar black hole, this would tear you apart before you even reach the event horizon. Near a supermassive one, you might actually cross the horizon fully intact and only then start to stretch. But spaghettification only happens to things that fall in. There's a far stranger, far slower threat for things that orbit nearby.
Black holes are supposed to be permanent. Nothing escapes them, not even light. But in 1974, physicist Stephen Hawking proposed something that contradicted that entirely. Black holes leak.
At the quantum level, empty space is never actually empty. Pairs of particles are constantly flickering in and out of existence everywhere in the universe, popping into being and instantly annihilating each other.
But near the edge of a black hole, something different can happen. One particle of the pair can fall in, while the other escapes outward. And from a distance, it looks exactly like the black hole itself is radiating particles into space.
This is Hawking radiation, and it means black holes are not permanent collectors. They are slowly, almost imperceptibly, evaporating. The catch is the timescale. A black hole with the mass of our sun would take longer than the current age of the universe, by a factor almost too large to write out, to evaporate completely.
But it means that even black holes, the most indestructible objects we know of, are dying. Just on a clock so long that the universe itself might not survive to see the end of it.
Every black hole we just discussed follows the rules. Stellar mass black holes form from dying stars. Supermassive ones grow at the centers of galaxies over billions of years. But in 2019, astronomers detected something that didn't fit either category. An object roughly 70 times the mass of our sun, sitting in a stellar binary system that was completely invisible. Nothing that massive should have been able to form as a black hole using the physics we understand, and nothing that massive should have stayed hidden. It was only detected because of its gravitational pull on a visible companion star nearby, the same way you'd notice an invisible person in a dark room only by watching the furniture move on its own. Whatever it is, black holes sitting in a mass range that, according to stellar physics, shouldn't be able to exist at all. A note so deep it takes 10 million years to repeat. A boundary where your own death freezes in time for everyone watching. An object slowly evaporating on a clock longer than the universe's entire existence so far. We've spent this much time staring into the dark, and the dark has barely blinked. Subscribe for more space videos.